Hello, Algebra 3 folks. Well, I almost made it through the year without failing to record the class, but today I forgot to hit record. So let me go over what we did in class briefly here. And I'll tell you, I looked back in my previous years. I do have a video of the second lesson. We have two lessons this week. The second lesson, I have a video from last year. I'm going to tack it on at the end of this because it goes into more detail in that lesson. But I want to look at the first lesson this week real quick, briefly with you. We have the fundamental theorem of algebra lesson. 8.05 and 8.06 are two lessons. The fundamental theorem of algebra, and this is nothing new to you, so we covered this kind of quickly in class today. It says if f of x is a polynomial of degree n, where n is greater than 0, f has at least one 0 in the complex number system. Basically what that's saying, if you have an equation that f of x equals x minus 3, and x is first degree, right, because x is the first degree, that means there's at least one 0. If it's larger than that, as long as it's greater than 0, you're going to have that. And also, we talked about with fundamental theorem of algebra, if it's x to the third minus 2x squared minus 4, something like that, that would have three zeros. X to the third would have three zeros. X to the seventh, if that's the largest exponent, would have 7 zeros. Whatever the largest exponent is the number of zeros, and those zeros exist in the complex number system, which means some of those may be imaginary, right? You could have imaginary zeros, so they may not, if you graph it, you may not see all the zeros because some of them could be imaginary. So this talks about, this is in very fancy math terms, it's just saying the same thing. If f of x is a polynomial of degree n, like say x to the fifth, n would be 5, so that you'd have some coefficient with an x to the fifth plus some coefficient with an x to the fourth plus blah, 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 all the way down to a constant. It will have precisely n linear factors, which means you could factor it to x minus something, x minus something, x minus something, x minus something, down to n number of factors. If it's x to the fifth, you'd have 5 different factors you can factor it down to, which means it would have 5 zeros. Okay, so it says if you have a first degree function, f of x equals x minus 5, it'll have 1 0, which is x equals 5. If it's a second degree, which is x squared, it'll have 2 zeros. In this case, x equals 4 and 3, because that'll factor. If it's third degree, 3 zeros. This one factors to have these 3. X to the fourth minus 16, this means it has 4 zeros. And if you factor this, which we could actually do, you get x equals 2, x equals negative 2, and two imaginary zeros with that. So just talking about the polynomial, fundamental theorem of algebra says a polynomial will have however many factors as the highest exponent. And then had little thing, find all the zeros. This one I actually did the first one in class. We took the x squared minus 625, or x to the fourth by 65. That is a difference of squares. These are both squares. This is 25 squared. This is x squared squared. So this factors to x squared minus 25 and x squared plus 25. And then we saw this is a difference of squares. This is 5 squared and x squared. So it factors to x minus 5x plus 5. This does not factor any further. It's just x squared plus 25. So with these factors, we can find out what the zeros are. The 0, if you set that equal to 0, x equals 5, right? Because 5 minus 5 equals 0. So that's one of our zeros. Negative 5 would be one of our zeros. And this, set it equal to 0. You subtract 25. You've got x squared equals negative 25. Well, taking the square root of both sides, you find that x equals 5i and negative 5i, because it's a negative 1 square root. Square root of a negative doesn't exist. It's imaginary. So these are our other two zeros, 5, negative 5, 5i, and negative 5i. And then this one, we could go back to where we did synthetic division and the a rational root theorem to figure out what numbers to divide in there and all of that. And we can find that. And it does do it on the check your answer sheet if you care to work that out and see if you're right. It talks about the rational zero system or the rational root theorem, synthetic division, and we can break all that down and find out. It also has a couple of imaginary zeros. And we talked about graphing polynomials, how we can tell, the y-intercept, the zeros is where it's going to cross the x-axis. If it's an even exponent, it's the largest. Both ends are going to point the same direction. If it's odd and all that. And we also talked about complex zeros occurring in conjugate pairs. That if you have a plus bi, then automatically you also have a minus bi as a zero. They always come in pairs. And here's a practical example. 3 plus 2i would be 3 minus 2i. You do not change the sign of the real part. You only change the sign of the imaginary portion of that. So starting the class, and talk about the factors, starting the class, we had an activity where I kind of quizzed the class to see how you did on this. I'm going to attach a link to that activity with this video. So if you want to look at that activity, it's kind of fun. AI will check you. It's got 6 little problems to make sure you understand the fundamental theorem of algebra and conjugate pairs for complex zeros. So you do have an assignment in Buzz on this. And I kind of went over this first one. Write a polynomial function of minimum degree that has real coefficients whose zeros include this. Has a 0 of 4, -8, and 2 plus 5i. And you have to find which one of these polynomials has those zeros. So I worked the problem similar to that on our paperwork, and I'll show you that. And I actually only listed these three zeros. If you had a 0 of 2, -5, and 2 plus I, right? 2 plus I. This is imaginary zero. So you should know automatically that means I have 2 minus I. So if I list 3 zeros and one of them's imaginary, there must be 4 because these always come in conjugate pairs. And then to figure out which polynomial would have these zeros, you change them to their factors. If 2 is a 0, then x minus 2 must be a factor. If -5, then x minus -5 must be a factor, which means x plus 5 because subtracting a negative. Then you would have x minus 2 plus I be a factor, and x minus 2 minus I would be a factor. So you have all those 4 factors, and then you just start multiplying them together. I multiplied these together first, and I multiplied these together before I started multiplying across there. Because when you multiply these two together, the imaginary part will go away. You have to distribute the negative, so it's x minus 2 minus I. See, when we distribute that, and when we distribute this one, it's x minus 2 plus I, because you have a negative I. But when you start multiplying these together, you get a plus ix, you get a minus ix, you get a minus 2i, you get a plus 2i, and those end up canceling each other out. So all of this would simplify to be x squared minus 4x plus 5. So I've multiplied those together, and I got this. I got multiplied those together, got this. Then I multiply those together, combine the like terms, and I end up with a 4th degree, which I should. I have 4 zeros, a 4th degree polynomial. And then we put this in Desmos just to show these were the zeros we could see in Desmos. These are imaginary, so those don't show up when we graph it. But when we entered this in the Desmos, those did show up. And then we had a problem on the assignment where you're supposed to factor this, write it in its factors. So I said, well, if we start breaking this down, it's x squared in both of those. So x squared plus 64. X squared plus 64 does not break down anymore. So what are the zeros associated with that? If we move the minus 64 to both sides, take the square root, these are the zeros. So the zeros, x squared would have 2 zeros. The zeros of this are 0, 0, 8i, and -8i. Then you put this back in factored form. This would be x minus 0 times x minus 0. So that's just x squared when you multiply those together. And then these factors be x minus 8i, x plus 8i. And you find the answer that has those four factors. They want this in fully factored form, which with the imaginary zeros, you got to find out what those zeros are so you can write them in factored form. And then you also have this lesson on rational functions and asymptotes. But since I have a video covering this in more detail, I'll let past Darren take that one over. So take it away.
All right, rational functions and asymptotes. Let's take a look at that, see what that entails. Scenic overlook. Remember, this is one of those lessons that we look at the scenic overlook and then we stop when we get here. This gives more information down here, than it goes into more detail and more sample problems, but all of it's covered up here in the scenic overlook. So up until now, we've really only worked with graphs that are continuous, right? There's no breaks in the graph. They go from one side of the graph to the other and all on to infinity, because the domain of polynomial functions has been all real numbers. So we're going to extend and look at functions that are not all reals. So a rational function, let's talk about what a rational function is. It's basically the quotient of two polynomials. So let me just write an example then. Let's pull up our little camera here, because before we get too much into this real mathy talk, I want to make sure we understand what this mathy talk is saying. Okay, so a rational function would be like f of x equals 2x squared minus 1 over 3x to the third plus x plus 4. Something like that, where we're talking about a polynomial expression on the top and bottom of a quotient, of a ratio, a fraction type looking thing. I'll lower this down a little bit so you get a better look at it. But this is what a rational function is. So when we talk about that, we're talking about something a little fancier than we generally have dealt with. So P of x divided by Q of x, right? Whatever those are. And this says where P of x and Q of x do not have any factors in common, and Q of x is not 0. See, that's the important part of this equation. If this is 0, we got a problem because we're dividing this by 0. We cannot divide by 0. So this would have a case where whatever x would make this equal to 0 would not be allowed, right? We would say x cannot be whatever that number is. We'd have to solve that. 3x to the third plus x plus 4 equals 0. And x would not allowed to be that because it wouldn't exist. So near the point that Q of x equals 0, the graph of the function may increase or decrease without bound. So let's take a look at what they're talking about. Let's just graph this equation that I just totally made up. So I have no idea what it's going to look like, other than it's going to have an asymptote wherever that denominator would be 0. So let's do 2x squared minus 1. And I need to put that in parentheses so it puts it all in the numerator. And that's going to be divided by 3x to the third plus x plus 4. Okay. So obviously, if x is 2, it looks like, or negative 2, I mean, see, negative 2, this graph is not going to exist at negative 2 because it said where it increases or decreases without bound. At negative 2, let's go ahead and put that on there. X equals negative 2. Oh, negative 1. Negative 1. Oh, this is going by 2. So, yeah, let me fix that. I don't like little minor grid lines. Make it go by 1s. So when the graph gets close to that point at x equals negative 1, the right side of the graph increases towards infinity very rapidly, where the left side goes towards negative infinity very rapidly. So this is an asymptote. It's a vertical asymptote because it does not exist. If we put negative 1 into there, 3 times x to the third, negative 1 to the third is negative 1. So it'd be negative 3 plus another negative 1 plus 4. So yeah, negative 1 would be what we would have on this. X cannot be negative 1 because that's what makes this 0 down here. And we also see the top. If we want to know the zeros, it would be where the numerator is a 0. So at 2x squared minus 1 equals 0 is where it's going to cross the x-axis. So we add 1, 2x squared equals 1. We've got to divide by 2. X squared equals 1/2. Square root of both sides. So x equals the square root of 1/2, which we could simplify, but we're just going to leave it at that. And when we see that, it's right there, 0.70711. That's where we see it come across the x-axis. And also at negative 0.70711, because the square root of that's going to have a plus and a minus. All right, so that is where it crosses the x-axis. So that's the zeros, and that's the asymptote at x equals -1 right there. So to see this, it says let's look at the function 1 over x. All right, we can do that. 1 divided by x. See, at 1 under x, if x equals 0, that's the asymptote, because that's where the denominator would be a 0 at. So you see right there at the y-axis, it goes way up on the right side, way down on the left side. The domain of the national function will occur at all real numbers except those values at x equals 0, right? That makes the denominator 0. So this goes all the way negative to infinity. The domain includes all x's, all real numbers, except for x equals 0. It says what happens as x approaches 0 from the positive and negative side? Well, we saw on here, it takes a sharp turn up and down. But if you just plug in numbers, when x equals -1, then the function equals -1, 1 over -1. When x equals -0.1, it's going to equal 10, because 1 divided by, excuse me, it's going to equal -10, because 1 divided by -0.01 is 10. So you get -0.001, -1,000, because it gets big really fast, because you got 1 divided by a very, very small number. And then on the right side, you got the same numbers as positives: 1, 2, 10, 100, 1,000. So you should graph this function to visualize it graphically, which we did, and see how it approaches on both sides. So the definition of vertical and horizontal asymptote states the line x equals a is a vertical asymptote if of the graph of f, if f of x approaches infinity or negative infinity as it approaches it from either side. So as we can see, when it approaches x equals 0, suddenly from either side of the graph, it's going to either approach infinity or negative infinity. So that tells us that this is an asymptote if we look at it on a graph. The line y equals b is a horizontal asymptote. If you see that, like right here, y equals 0 is a horizontal asymptote, the x-axis, because as the graph is going to negative infinity, it's approaching closer and closer and closer. Oh, it's picking up back there. It approaches closer and closer and closer the farther it goes. And then on the other side, it's coming in from the top, but it's getting closer and closer. But it will never touch asymptotes. Now, that's not necessarily true with the horizontal asymptote, because these rational graphs can do something really weird. Sometimes you may have this dip below the asymptote and then come back and approach it forever without touching it. But it may cross it first, because rational expressions do some really weird graphs. It says, review your text to see examples. So for the rational function, p of x divided by f of x, q of x, says where p and q do not have any common factors, the following applies. The graph of f has vertical asymptotes wherever the denominator equals 0. And the graph has at most one horizontal asymptote. So this is what we need to, and then they just have some example problems. This is what we need to dig more into. How do we figure out what the horizontal asymptotes are? Okay. We need to put this in our notes because they don't have a really good definition for us in the lesson there that that we're going to be able to read and understand simply. So for vertical asymptotes, uh, x equals whatever x would make the denominator equals 0. So our asymptote is going to be whatever x that would make, like, for example, that right there. So we're going to just highlight that as an example. Vertical asymptotes. X equals denominator equals 0. So for example, right there, for this one, we have a nice example. Horizontal, calculating horizontal asymptotes S are based on the oh, degrees of the numerator and denominator. Okay, so the horizontal asymptote, that's this direction, are based on the degrees of the numerator and denominator. So, for example, we need to illustrate this. If we have f of x is, let's do 2x over 4x squared. Here's our first situation. Since degree of denominator, what is the degree of the denominator? Well, let's get our little pin here. All right, it's squared. The degree of the denominator is 2, is greater than degree of numerator, which is, it's an assumed 1, right? Because it doesn't have 1. It's a 1. Horizontal asymptote is y equals 0. It will have a asymptote at y equals 0 because the degree of the denominator is larger than the degree of the numerator. That's the first case. The second case, if degree of numerator is greater, bet you know where I'm going with this, huh? Then degree of denominator, there is no horizontal asymptote. Oh, yeah, that's right. Numerator is greater. The numerator is greater than the degree denominator. There's no horizontal asymptote. So that would be in the case of f of x equals, let's say, 3x to the third over 2x squared plus 1. We've got a third degree in the numerator and a second degree. This will have no horizontal asymptote. Let's take a look at that just so we can see on a graph what we're talking. So first, let's do the first one that I did. It was 2x divided by 4x squared. And there's that horizontal asymptote at y equals 0. Then the second one we just looked at was 3x to the third. And it's divided by 2x squared plus 1. So there's no horizontal asymptote. It continues from negative infinity to infinity. No horizontal asymptote. If I suddenly change to make that fourth degree on the denominator where it's larger, now we're back to that horizontal asymptote that it approaches. But now I told you it gets weird. Look, it actually does cross the asymptote, but going both directions on the ends, it's approaching y equals 0 as a horizontal asymptote. All right, that leaves one case that we haven't looked at, right? There's one other possibility. If the degrees are equal, then the horizontal asymptote is the ratio. Oh, you're thinking, oh, we're using big words here. Of the coefficients of the largest terms. So we're definitely going to write down an example of this. So if we have, so the degrees are equal, then the horizontal asymptote is the ratio of the coefficients of the largest terms. And what we're saying is if we have, let's say 2x to the third plus x squared, just for the fun of it. And down here, we've got 8x to the third minus 1. Look, the degrees are equal. These are both third degree polynomial expressions. So in that case, this is the largest term. We take the ratio of the coefficients. So the asymptote is y equals 2/8, which of course we simplify to 1/4. That would be the horizontal asymptote. If they're equal, we just take the coefficients and set them up as a fraction. So let's put this in Desmos and take a look at that. So the top was 2x to the third plus x squared. And then the bottom one was 8x to the third minus 1. All right, minus 1. Change this to the third. And I made this an 8. So this is the y equals 1/4 is the horizontal asymptote. See, as it's getting closer and closer, that's the line that it's getting closer to on both sides. You just take that coefficients. Now, if we want to change the coefficients, let's say that the coefficients are f of x equals, we'll say this is 12x to the fourth over 2x to the fourth minus 1. These are both x to the fourth, so the horizontal asymptote is going to be at 12 over 2, because that's the coefficients, which means it's at y equals 6, because 12 divided by 2 is 6. So let's look at that. Let's change this equation to be y equals 12x to the 4th divided by 2x to the 4th minus 1. We have a horizontal asymptote. Now, see, this is not a horizontal asymptote. We have two vertical asymptotes. So we have a vertical asymptote at -1, and we have a vertical asymptote at 1. Or actually, it looks like it's probably smaller than that, because it does. It's like a 0.8 or something, or 0.9 vertical asymptotes. But the horizontal asymptote's up here at y equals 6. That's what we were calculating. What's the horizontal asymptote? The vertical asymptotes would be wherever 2x to the 4th minus 1 equals 0. We could calculate that. So we can see on the graph, it's less than 1. It's some decimal number. But that is how we find the horizontal asymptote. There's 3 cases. Numerator less than the denominator, if they're equal, or the numerator is a higher degree than the denominator. All right, let's see. Let's take a look at these. What are the vertical asymptotes? What's the horizontal asymptotes? X minus 3 over x plus 2. Let's talk about the horizontal asymptote first. The degree of the numerator is 1. It's x to the 1st. The degree of the denominator is x to the 1st. What's the coefficients? Well, they both have a coefficient of 1. So it's 1 over 1. So the horizontal asymptote for this first one is just going to be y equals 1. And if we're not sure, we can always graph it. But let's look at the vertical asymptote also. The vertical asymptote is wherever the denominator equals 0. So x plus 2 equals 0. That's when x equals -2. So this will have a vertical asymptote at x equals -2 and a horizontal asymptote at y equals 1. So let's look at that. X plus 3. 3. No, get rid of all that. Divided by x minus, x plus 2, whatever, plus 2. Plus x minus 3 plus 2. Okay, minus 3. So we said there's a vertical asymptote at x equals -2. And there it is. We see it in green. That's that. And we said the horizontal asymptote is y equals 1. And there it is. So look at Desmos to double check ourselves. That is exactly correct. Those are the asymptotes for this rational function. Okay, look at this one, x plus 1. X squared minus 4. In this case, x to the 1st degree, x second degree, the denominator is larger than the numerator. So if we go back to our notes and say, okay, the denominator is greater than the numerator, so this will have asymptote at y equals 0. Horizontal asymptote. So this middle one is a horizontal asymptote at y equals 0. And x squared minus 4, that is where the vertical asymptotes will be. So wherever x squared minus 4 equals 0, add 4. Wherever x squared equals 4, square root. So x equals plus or minus 2. There's 2 vertical asymptotes, one at 2 and one at -2. So let's take a look at that. Change this one to x plus 1 on top. Change this to x squared minus 4 on bottom. And we said there's 2 vertical asymptotes, one at x equals 2 and one at x equals -2. And we can see those. Let's turn off the asymptotes or we can just see the original graph. See, we got a 3-piece graph because you have a horizontal asymptote at x equals 2 right over here. That's going to divide those 2 pieces. And then we have one at -2 over here. And then in the middle, you've got this piece that goes towards infinity on the left and negative infinity on the right. And then we said that this was at y equals 0. So it's just the x-axis for the horizontal asymptote. And this one's not going to have a horizontal asymptote because the numerator is second degree and the denominator is only first degree. But we will have a vertical asymptote at x equals -1. So let me see if this works where you can actually check your answers on that. Yes, it does look like it works. Oh, so there it is, even including the graphs. If it loads the graphs, it's still loading. But yeah, no horizontal asymptote in the last one, x equals -1. But it's taking forever to load that. I'm not going to wait on it. That's the whole lesson. We're just looking at the vertical and horizontal asymptotes. Oh, state the domain. That's what possible x's they are, right? Well, that was the first thing we talked about, is it's going to include all x's from negative infinity to infinity, except for any x that would make the denominator a 0. And if you're not sure, just graph it. And say, are there any x's that it cannot be? 13 over 10 minus x. 13 over 10 minus x. Yep, look, there's a place where there's an x that's not included. It goes to negative infinity and goes to infinity, except for where x equals 10 right there. State the vertical asymptote. That's anywhere that the denominator equals 0. What's the horizontal asymptote? Remember, that's based on the degrees. State the horizontal asymptote, again, based on the degrees. And give an example. So you're going to make up your own on this bottom one. Give an example of a rational function that has no horizontal asymptote, and the vertical asymptote is x equals 1. So there's an infinite number of correct answers there. You just got to go back and look at, how do I make it where it has no horizontal asymptote? And how do I set the vertical asymptote at x equals 1? Five questions. As long as you got in the notes how these work, the degree of the numerator and denominator determines the horizontal asymptote, and whatever the denominator makes 0, whatever x that is your vertical asymptote. So hopefully you won't have a lot of trouble with this. 5 questions. Try to just simplify it down. We're not looking at, there's other things you do with rational functions, like we're holes in the graph. We're not talking about holes and dealing with all of that. We're just looking at the asymptotes. And next week, we'll look more into the graphs of that. And that's our last 2 lessons we're going to have. All right, guys, I'm going to let you go. There's no need to keep you for the rest of the class. It's too close to summer for that, right? We're already in the May. It's the 6th. We don't have much left. Seniors, I'm excited for you. You're getting there. You're right at the end. We'll get exemption emails out to you. If you got any questions, email me. This is a B-Day Friday, so I'll be here Thursday and Friday. If you got questions or anything you need help with, come see me. Otherwise, have a great week.